This is the Unit 3 seminar on solving exponential and logarithmic equations. The very first table is just a review of the rules, the laws that we went over on scheduled days with a few examples. So not necessary to copy all of it, just make sure you have an idea and you understand what is up here. Now, in today's seminar, I am going to be going through some questions, logarithmic equations, that are either challenging in your unit guide or will definitely appear in some form on your test for Unit 3. Good news is, especially if you took the in-class for the Unit 1-2, I heard it was quite simple last class. Unit 3 is very much a continuation of Unit 2, which means applying the same logarithmic rules to equations and formulating word problems. However, the word problems get more difficult. There's a continuation of the same theme: intensity of sound, intensity of light, Richter scales. We're going to do a population question as well. And I really want, in the Unit 2 seminar, we spoke about the natural logarithm, and which is taking the log of Euler's number E. We're going to actually use and apply population questions. Do you guys need to come in? Yes. This is Unit 3. Did you already come?
I went to this
Oh, so you don't need to. Well, you can come if you want. I'm just going through test questions. Okay, it's up to you. Okay, sorry. So we're going to start off, like we always do, pretty simple, and then we're going to move into more difficult questions. Going to move into more difficult questions. The last one before we tackle word problems, I feel like the most scariest thing for you guys are fractions and radicals. So we're going to tackle one logarithm question that has both of them in it, as well as one that needs to be converted into the quadratic equation. So you're going to find that you're using your grade 10 and 11 skills frequently to tackle these type of equations. Okay. So this is another thing. It's a corollary, another item. Corollary to the power rule. We've already dealt with the change of base formula, but this is something I didn't necessarily go over on scheduled days. But if the power rule says that we move our exponent to the front of the logarithm, when you have a radical expression, the index, right, can be written as a power in terms of fractions, right? So the corollary to the power rule means that this is true, and we're going to use that rule to tackle one of the questions in the seminar today. So remember, kiddos, I'm taping, so I need volume to be reasonable. Okay. Start off very simple, because I don't know what all of you were taught during scheduled days. So, very basic. 2 to the power of x plus 1 is equal to 7. I want to solve for the x. The x is in the exponent. I forgot to corroborate my smartboard. Give me 1 second. Disappeared. Okay, so first thing, obviously, I'm going to do is what? Take the log of both sides. So I'm going to rewrite this question as log 2 to the power of x plus 1 is equal to log of 7. I said this is a very basic question. What is the next rule that I should apply for this question? Smartboard is really slow today. What's the next rule? Dave? So I'm applying what rule? The power rule, good. So I'm going to bring the x plus 1 down, because remember, my goal is to isolate the x at the end of the day, is equal to log 2 is equal to log 7. Now, to isolate my x plus 1, what should be my next logical step? What's the next logical step, Kyle? Yes, divide both sides by log 2. So I have x plus 1 is equal to log 7 divided by log 2. And finally, to solve, what is the final step? Yep. Subtract log A minus log B? Well, first we want to isolate the x, right? So I have to move this positive 1 over to the other side. So x becomes equal to log 7 over log 2. That's actually something we could punch straight away in the calculator. We don't have to move back to the subtraction rule. And then just subtract 1 from your answer, which will give you the final answer. Can someone punch that into your calculator to give me an exact answer, Georgia? The whole thing. 1.81? 81. Okay, perfect. So, what about, it gets a little bit more difficult if we have x expressions as our exponent in binomials on both sides, the left-hand side as well as the right-hand side. So first step is exactly the same. I'm going to take a log of both sides. Daggy, what rule am I going to apply next?
The power rule.
Good, the power rule. But remember, the last question I applied the power rule once. Now I'm going to apply the power rule twice. I'm going to bring the x plus 1 and the x minus 1 down in front of the logarithm. Now this is where students get confused. Because last time, since the x was only on one side, we were able to divide both sides by the logarithm in order to get rid of the x. However, now that I have x variables on both sides, before I can isolate the x, I have to apply what property? You learned it in grade 9. Starts with a D. Distributive property. So I have x times log 2 plus log 2 times 1 is going to equal x log 3 minus log 3. Distributive property. Now I can shuffle things around in order to isolate all my x terms on one side. So I know that and that are my x terms. I want them on one side. So I have x log 2 minus x log 3 is equal to negative log 3 minus log 2. Now you see subtraction, so you're going to be tempted right away to apply my subtraction rule and change them into products, but we don't want to do that because we have these x, we have an x in this term and an x in this term. I want to take the greatest common factor out, which is my x. So I'm going to factor my x out. So I'm left with log 2 minus log 3 is equal to negative log 3 minus log 2. And now to isolate the x, I can simply divide both sides by log 2 minus log 3. So those cancel out, and we have an expression for x that we can now solve. Does that make sense to everyone? So the key thing I want to point out, if something you're doing, there's multiple ways of solving questions because of the different log rules we have. If something is not working out or you get stuck, then go back and undo it. Try to apply the distributive property. Try to factor, okay? Don't get frustrated if you run into a brick wall. Just apply a different rule to help you get out of the situation. Okay, next question is very, very, very important. Put lots of stars next to this question because you're definitely going to see some version of it on your test. And the key reason why this is important is the hint for you is if you see that the first term is raised to the power of 2x, and the second term is raised to the power of x, and the bases are the same. That is a hint, no matter what the base is. If you see 2x and an x, the bases are the same. It's a hint that you're going to have to use quadratics to solve. So first of all, I'm going to rewrite this question as 3 to the power of x, because I want both of these expressions to have a common base. 3 to the power of 2x can be written as 3 to the power of x to the power of 2. Does everyone agree with that? Because the rule is to multiply your exponents. So I'm going to keep that to slightly alter the way that I'm expressing it. Minus 5 times 3 to the power of x. Bring the negative 6 over to the other side, so I have positive 6 is equal to 0. Okay, that's the first thing I'm going to do. Really focus on the fact that now the question is written so that the bases are exactly the same. Instead of I have the same base with different exponents, now my base and the power is exactly the same. So I'm going to let 3 to the power of x, I'm going to set that equal to y. So let 3 to the power of x be equal to y. So now I can, if I do that, I can rewrite this complicated exponential equation in terms of no exponents, well, hardly any, y squared minus 5y plus 6 is equal to 0. What type of equation is this? Sorry? What type of equation is this? You saw this first in grade 10, Columbola. A trinomial, which represents a quadratic equation. How would you solve a quadratic equation? Yep. By factoring, either trial and error, or if you can't use trial and error, the quadratic formula. So I went from an exponential equation I really didn't know how to solve to something that is very simple for me to solve. If I factor this, I get y minus 3 times y minus 2 is equal to 0. That means y is equal to positive 3 and y is equal to positive 2. So I'm going to ask you, can I stop here? Is my question done? Can I leave it and move on? Why not? What do I need to do next? What do I need to do next? Lethem, what do you think? What was y equal to? Yes, y is equal to 3 to the power of x. So I'm going to substitute that back into the equation, but now I have something that is actually doable, something I know how to solve. So instead of y is equal to 3, I know that y is equal to 3 to the power of x. So 3 to the power of x is equal to 3. I don't even need logarithms to solve this because I know that 3 is the same as 3 to the power of 1. I can cancel my bases. So x is equal to 1. That is one value. X is equal to 1. Now for 3 to the power of x, when I set that equal to 2, now I need logarithms to solve this. So I'm going to rewrite this as log 3 to the power of x is equal to log 2. Then I'm going to apply the power rule. Remember, this is an exponent. So it becomes x log 3 is equal to log 2. To solve for x, I'm simply going to divide both sides by log 3. So can someone give me a value of what log 2 divided by log 3 is? What is log 2 divided by log 3, Dave? X is equal to 0.631? 0.631. Thank you, Dave. So I have two possible values for x that will satisfy my exponential equation. Because these are both positive values, right? No negative values, they work. We can accept both answers. Is everyone okay with this? Yes? So put extra stars next to this question. For sure that's going to come up in the future. Okay. Let's do one with multiple logarithms. We're going to be using quadratics again. And then we'll tackle one with a square root and fraction. And then we'll move on to word problems, okay? I know some of you are really stuck on the word problem. For questions like this, it's very important that we have to take my binomials, and this is something everyone forgets to do on the Unit 3 test. I don't know why, because we really stress it. These binomials actually represent restrictions per se on the equation. So for example, this means if I set that to x plus 3 has to be greater than 0, this will give me that x has to be greater than negative 3. And over here, x minus 3 is greater than 0, x has to be greater than positive 3. But the one that we're really going to pay attention to, obviously if x is greater than positive 3, it's going to be greater than negative 3, right? But if it is not greater than negative 3, it's not going to be greater than positive 3. So we really take the smallest restriction as the absolute one. Basically, our answer has to be greater than negative 3. Okay? If it's greater than negative 3, it follows that it'll also be, it has to be greater than negative 3, okay? Okay, so first thing we're going to do, on the left-hand side, I'm going to keep the common log to the base of 2, and what am I going to do with my binomials? Big room, someone needs to know. What am I going to do with my binomials now? Because we have addition, so... Yes, exactly. I'm going to multiply them together. So put some square brackets. And I'm going to multiply x plus 3 times x minus 3 is equal to 4. So that's the same as log to the base of 2. I have a difference of squares situation there. So that's x squared minus 9 is equal to 4. Now, I've taught you this many times. If I have a log on one side and not the other, and now I want to get rid of the logarithm, I can't just take the log of both sides because then I would be doubling this. It wouldn't be balanced. So I want to get rid of that logarithm. How do I do that? Based on the first rule you learned. Yeah. Yes. You're taking this base, the base of your logarithm, and you're raising it to this number on the right-hand side of the equation. So I can write it as x squared minus 9 is equal to 2 to the power of 4. Does everyone understand that? X squared minus 9 is equal to 2 to the power of 4. If we solve that further, x squared minus 9, what is 2 to the power of 4? 16. So that means that x squared is going to be equal to 16 plus 9. X squared is equal to 25. X is equal to plus minus 5 because I'm taking the square root of 25. Am I done? Is this the final answer? Why is this not the final answer? What is wrong with this? Yep. Yes, exactly. Greater than negative 3. So since, I'm going to actually write that down in full so you understand this. Because positive 5 is greater than 3, but since x has to be greater than negative 3, x is equal to negative 5 fails, right? However, my final answer is going to be x is equal to positive 5 because that is, since this answer satisfies the condition that x is greater than 3 as well as x is greater than negative 3. Satisfies both conditions. Does that make sense? Okay. How much time do we have? Half an hour? So let's quickly go on to deal with this problem. Ha ha ha. And then we're going to do some word problems. So I'm going to zip through this question. I just put this one up here to make you realize that if you know your laws, this is not difficult. If you know all your laws, so the first thing I'm going to do, log. When I have a radical equation, so I have this equation x squared plus 48x, it's the cubed root of that. How can I express the cubed root in terms of a power? Kyle? Yes, to the power of 1/3 is equal to 2/3. Question still looks scary, but at least you've got rid of your radical. Now, what is my base here? What is my base? 10. Good. When you don't see a number there written as a base, then your base is already 10. I only have a log on one side, right? So you already know if you have log on one side, not on both sides, to get rid of the logarithm, I'm going to take my base of 10 and I'm going to raise it to my other side in terms of my right hand side. So this becomes 10 to the power of 2/3. 10 to the power of 2/3 is equal to x squared plus 48x. Does everyone agree with that? X squared plus 48x to the power of 1/3. Everyone's okay with that? Yes? Okay. Now, we're going to cube both sides to get rid of the rational exponents. Okay, I'm going to say that again. I have a common denominator of 3. So if I cube both sides, I multiply both sides by to the power of 3, I'm going to get rid of those rational exponents. Remember, this is a very challenging question. This is not a simple question. I just want to show you how you know what it takes to solve this question. So I have 10 squared now is equal to x squared plus 48x. What is 10 squared equal to? 100. So I'm going to bring everything over to one side. So I have 0 is equal to x squared plus 48x minus 100. Okay? We can either now use the quadratic formula, or you can use trial and error to solve this. I use trial and error. So 0 is equal to x plus 50 times x minus 2. Those are my two binomials. That means that x is equal to positive 50, or x is equal to positive 2. And then we can check that if it satisfies the equation. If you plug it back in to log cubed root of x squared plus 48x is equal to 2/3, you will find that both are solutions to this question. So they both satisfy this is not positive 50, x is equal to negative 50 will satisfy this equation because we are squaring it, and x is equal to positive 2 also satisfies the equation. So very important to plug it back in to check. Is everyone okay with that one? So if you do see a rational exponent on both sides, you know, multiply it by the LCD or LCM, lowest common multiple, raise it to that power to get rid of it, okay? Okay, word problems now. I'll give you a second to copy down the first one. Radioactive substances. Is that you, Daggy? Okay, so we have 200 grams of radioactive substance. You guys can take pictures of the question too if you want to copy it later. 16 days later, only 12.5 grams remain. What is the half-life of radium? Okay, so we're going to first set it up in terms of our generic exponential equation, AB to the power of x. But because when we're talking about half-life, we also, in our unit 617 of MCR, we learned this formula. AL, which is the amount of substance that remains after the experiment, is equal to AO, the original amount of the substance that we started off with, 1/2 to the power of my time over my half-life. That's what we learned last year, right? So whenever we're talking about the half-life or something, we pretty much use this formula. So I know that after 16 days, 12.5 grams remain. So I'm going to keep that as my AL. My AO is what I started off with originally, 200 grams. And then I have my base is 1/2 to the power of, the experiment took 16 days for this result to happen, and I'm trying to solve for my half-life.